Hi guys, here's a video of our lesson on recursive sequences just in case you need to see it again. So what we're focusing on today are recursive sequences. So we've already dealt with arithmetic sequences where you're adding the same number every single time, and we also have geometric sequences where you're multiplying by the same number every single time. But let's say the pattern is different. So instead of adding the same thing every time or multiplying by the same thing every time, we did a combination of both. So for instance, you were adding 2 and subtracting 5, or adding 2 and multiplying by 10, stuff like that. That is a recursive sequence. So the definition of recursive formula, each term is formulated from one or more previous terms. So for a recursive formula, we use the previous terms to find new terms. So what is the difference between a recursive formula and an explicit formula? Recursive formulas use previous terms to find new terms. So for instance, if I wanted to know the 20th term of a sequence, I would use the 19th term to find the 20th term. Okay, so you use your previous terms to find any new term. For an explicit formula, explicit formulas allow us to find any term of a sequence just by knowing the term number. So you can find any term by plugging in n. So if I want to know the 20th term, all I would have to do is plug in 20. So explicit formulas are better for bigger sequences, where if you just wanted to know like the 20th term, you just had to plug in 20 for n. Recursive formulas, you would have to know all of the terms beforehand to be able to find a new term. So if I wanted to find the 20th term, once again, I would have to know the 19th term. And the 18th term and so forth, since you use the previous terms to find new terms. So we looked at explicit formulas for arithmetic and geometric. So our explicit for arithmetic was an equals a1 plus d times n minus 1. And then for geometric, it was an equals a1 times r to the n minus 1. So these were the explicit formulas, because we could be able to find, we would be able to find any term by plugging in the term number n into the formula. So now we're going to look at recursive formulas. So a recursive formula is built off of previous terms. So let's start by labeling what we know. A1 represents the first term. An represents the nth term. D, since it's arithmetic, is your common difference. And this an minus 1 is what's new. Okay, so an minus 1 means the previous term. So if the term that I'm trying to find is an, the previous term is an minus 1. Okay, so an minus 1 means the previous term. Same thing for geometric sequences. A1 represents the first term. R is your common ratio since it's geometric. An is the nth term. And an minus 1, again, that's what's new today, and that's the previous term. Okay, so actually using a recursive formula. So the first thing we want to do is we want to label if the formula is arithmetic or geometric, and how do we know? So for letter A, we have A1 equals negative 23, AN equals AN minus 1 minus 1.5. And then for letter B, we have A1 equals 24, and then AN equals AN minus 1 times 1/4. So if you look at letter A, we are subtracting 1.5. So if you're ever adding and subtracting, that is arithmetic. So we're going to go ahead and label this as arithmetic. And then for part B, we are multiplying by 1/4. Multiplication indicates geometric, since we're multiplying by the same thing every time. Okay, so my first term is negative 23, so we're good on that. If I want to find my second term, once again, this means your previous term. So if I'm trying to find my second term, my previous term is A1. So I'm taking A1 minus 1.5. So negative 23 minus 1.5 is negative 24.5. If I'm trying to find my third term, I take the previous term, which is A2, minus 1.5. So negative 24.5 minus 1.5 is negative 26. Okay, and then the pattern continues. So I want to find the next four terms. So we already have the negative 24.5. We have the negative 26. The next term, I'm still subtracting 1.5, so that's negative 27.5. And then finally, negative 29. So you're using the previous term and subtracting 1.5 to get your next terms. And then for letter B, if I want to find my second term, I am taking my first term and multiplying it by 1/4. So that is going to give me 24 times 1/4 is 6. And then if I want to know the third term, I'm taking my second term and multiplying it by 1/4. So 6 times 1/4 is 3/2. Okay, and then the pattern continues. So we want to find the next four terms. So we have the 6, we have the 3/2. I'm going to take my third term, multiply it by 1/4. That gives us 3/8. I'm going to take that and multiply it by 1/4, and that gives me 3/32. So a recursive formula is just another way to represent a sequence, and it tells you what the first term is, and it also tells you what the pattern is. So for instance, for letter A, our pattern was to subtract 1.5, and then for letter B, our pattern is to multiply by 1/4. The next thing that we're doing is switching back and forth between the different forms. So starting with a recursive formula and then changing it to an explicit formula and vice versa. So we need to be able to recognize which formula is which. Your recursive formula is always set up in two parts. So for A and B, both of those are written recursively. So we'll go ahead and label this. So recursive formulas are always labeled in two parts. You have your first term and then your formula for the sequence. You have your first term and your formula for the sequence. Another way that you can tell you have a recursive formula is this AN minus 1, and over here AN minus 1, because recursive formulas are always built off of previous terms, and AN minus 1 means the previous term. So for these two problems, we want to change it to an arithmetic explicit formula. So if you recall, your arithmetic explicit formula looks like this. So if we're writing the formula, we need to know two things. We need to know our first term, and we also need to know the common difference. Well, the first term is already laid out for us. First term is 0, so I can take 0 and replace it for A1. Our common difference is whatever we're adding and subtracting every time. And if you look at the formula for this sequence, let's erase some of this writing, you're taking your previous term and you keep subtracting 3. that is your common difference, okay, because you're subtracting 3 every single time. So since we are subtracting, I'm going to go ahead and write that as minus 3 times n minus 1. This we can go ahead and simplify further, so I'm going to distribute. That gives me 0 minus 3n plus 3, since we're multiplying a negative and a negative. So your final explicit formula is an equals, after we combine like terms, is 3 minus 3n. So we started with this recursive formula, and then we ended with that explicit formula. Okay, so we changed from explicit to, we changed from recursive to explicit. And we're going to do the same thing over here. So again, we're going to start with our first term, which was 3. Our pattern for this is we are adding 5, so that means our common difference is 5 times n minus 1. That we can go ahead and distribute. So that gives me 3 plus 5n minus 5. Combine your like terms, that leaves you with negative 2 plus 5n. And that is your explicit formula. So we started with this recursive formula, and we ended with that explicit formula. For C and D, we're going backwards. So this right here I'm going to label as explicit. Same thing over here, I'm going to label this as explicit. Okay, so once again, to be able to find any formula, we need to know 2 things. We need to know what our first term is, and we also need to know what our common difference is. Okay, that's how we can set up the formula. Now, when we have the explicit formula, terms for a sequence are found by plugging in the term number. So if I want to find the first term, I'm going to take 1 and plug it in for n. So 1.3 minus 0.4 times 1 gives us 0.9. Now if we go back to this example over here, looking at this to this, our common difference ended up being that minus 3. Okay, and if we look at where it is in our explicit formula, that minus 3 is what's sitting right in front of the n. Okay, so your common difference in an explicit formula is always what is in front of n. So in this case, my common difference is the negative 0.4. Okay, so now that we have those 2 pieces of information, we can go ahead and write the recursive formula. So recursive formulas have 2 parts. You start by listing your first term. So A1 equals 0.9, and then you have the formula for the sequence. So an equals my previous term, which we write as an minus 1, plus your common difference. Our common difference is negative 0.4, so that's minus 0.4, and then that is your recursive formula. So we started with this explicit formula and we changed it to that recursive formula, so just switching the forms. Letter D, we're going to do the same thing. So I need to find my first term. My first term, I'm going to take 1 and plug it in for n. So 2.9 plus 0.3 is 3.2. My common difference is what's in front of n, so that's 0.3. And now that I have those 2 pieces of information, I can go ahead and write the formula for the sequence recursively. So A1 equals 3.2. And then the formula for the sequence, an equals my previous term, which is an minus 1, plus 0.3. And then that is your recursive formula for the sequence. Okay. So the next one we are looking at is the geometric formulas. So once again, I'm going to go ahead and label these. These are recursive. And again, you can tell because it's written in two parts, and you also have the previous term embedded in the formula. So that's recursive, and this is also recursive. Okay, so explicit formulas for the geometric look like this. AN equals A1 times R to the n minus 1. So we already have our first term. It's 6, so I can replace that in there. Our pattern is we are taking our previous terms and multiplying it by -3. So whatever you multiply by each time, that's your common ratio. So our common ratio for this is -3 to the n minus 1. Now with geometric explicit formulas, there's no other simplification that we can do. So that is our final answer. So for geometric, it's almost like you're rearranging the numbers in a different form. So there is your recursive because it has two parts, and then we changed it to explicit, and once again explicit would allow us to find any term by plugging in the term number for n. Okay, so explicit is always just a one-line formula that you can plug in your term numbers for n. And then same thing for part B. So my first term was 3, so I can replace my first term in the formula. And then this is your common ratio, so 0.75 to the n minus 1. And then there is your explicit formula. So explicits and recursive going back and forth for geometric is a little bit easier than what we did for arithmetic, because if we go back to arithmetic, we had more work to do, because when we set up this formula, we put our first term and our common difference, we had to simplify it further. But when we do that for geometric, there's nothing else to simplify because this right here is an exponent, so you can't distribute or anything like that. So for C and D, we have the explicit formulas. So I'm going to label this as explicit. And that looks a little weird. Fix that so that it is an I. And then this one's also explicit. So recursive, we have to write with the two parts. We need to start by listing our first term. Here is your first term, so it's 1.3. And then your formula for the sequence is you are taking your previous term, an minus 1, and multiplying it by your common ratio, which is -0.4. And there you go. Same thing for letter D. Here is your first term, so A1 equals 2.9. Formula for the sequence is you are taking your previous terms, which is an minus 1, and multiplying it by your common ratio, which for this is 4.3. Alright, so geometric, when we look at the explicit formulas, the first term is already presented to us. So for this one, our first term was 2.9. It was already in the formula, which is why it's easy to do. If we go back to arithmetic sequences and we look at this explicit formula that I am circling in black, our first term was not listed, okay? Our first term is not 1.3. Try not to make that mistake. Our first term we have to find by putting in 1 for n. Okay, so that covers arithmetic and geometric recursive sequences. Now let's look at a sequence that is not arithmetic or geometric. So Mr. Yazaki discovered that there were 225 dandelions in his garden on the first Saturday of spring. He had time to pull out 100, but by the next Saturday there were twice as many as he had left. Each Saturday in spring he removed 100 dandelions, only to find that the number of remaining dandelions had doubled the following Saturday. So let's see what's happening here. So he starts with the 225, he pulls out 100, and then it doubles. And then the next Saturday, he pulls out 100, and then it doubles. So we are not adding the same number every single time, solely adding the same number every single time, or multiplying by the same number every single time. It's a combination of both. He's pulling out 100 and then it's doubling. He's pulling out 100 and then it's doubling. So our recursive formula for this is not going to follow what we had for arithmetic or geometric. It's going to be its own formula that matches this pattern. So again, for recursive formulas, we always start by listing the first term. So on the first Saturday, he had 225 dandelions. And what's happening is he is pulling out 100. So that means he is subtracting 100. So he's taking the previous amount, subtracting 100, and then that amount doubles. Okay, so he's taking out, so he starts with the 225, he pulls out 100, and then it doubles. So we have our previous term, which is the an minus 1. He pulls out 100, and then it doubles, which means it's multiplying by 2. So part B says to find the number of dandelions Mr. Yazaki would find on the 5th Saturday. So we have to use our previous terms for this. Our first term is the 225. If I want to know how many he has on the 2nd Saturday, I would take that 225 and subtract 100 since he pulls out 100, and then that we would have to double because after he pulls out the 100, it doubles. So then that's going to give us 225 minus 100 times 2 is 250. So on the 2nd Saturday, there are 250 dandelions. If I want to know the 3rd Saturday, I'm going to take the amount on the 2nd Saturday minus 100 and then multiply by 2, because again, he's pulling out 100, but what happens after he pulls out 100 is that it doubles. So that's 300. And then for the 4th Saturday, same thing. He starts with the 300, he pulls out 100, and then the dandelions double. So 300 minus 100 is 200, times 2 is 400. And then for the 5th Saturday, you're taking the amount that he had on the 4th Saturday, which is 400, minus 100, times 2, because he pulls out 100, and then for some reason it doubles. So 400 minus 100 is 300, times 2 is 600. So on the 5th Saturday, he has 600 dandelions. So again, for this recursive sequence, it was not arithmetic or geometric because we were not adding the same number every single time and only doing that, and we were not multiplying by the same number every single time. Okay, it was a combination of both, where he was pulling out 100, so subtracting 100, and then it doubles. Okay, so this is kind of its own recursive sequence, but it is recursive because we have to use the previous terms to be able to find the new terms. Alright, so that covers our lesson on recursive sequences. Have a great day.